Reference geometries can be used to assign various simulation objects including doping profiles, boundary conditions, sources and monitors to any desired volume or surface in the simulation. This will give users freedom to apply attributes to arbitrary geometries. There are two major types of reference geometries: volumes and surfaces. Obviously, in a two-dimensional simulation, a volume will translate into a surface, and the surface will be equivalent to a line. Now imagine there is a spatial overlap between two objects in your simulation. Reference geometries will enable users to define an attribute such as a doping profile for a partial volume of simulation with any desired geometry, like the highlighted red area, for example. Or for instance, a simulation object such as a monitor can be assigned to the plane object to monitor the desired variable at the cross-section of the sphere object shared between the two objects. Let's explore a few examples to give you a better idea about the application of reference geometries. We will demonstrate the application of reference geometries using an example of a core shell semiconductor structure. In this example, I have defined two materials in my simulation, one as the core material and the other as shell. Each one of these materials has been assigned to a geometric object forming a core shell structure. Let's start with surface type reference geometries. I will use a surface recombination boundary condition from the charge solver as an example. The reference geometry can be assigned from the edit window of each object. Note that I have switched to partition volume mode, which will help us to find and visualize the reference geometries we need. The first surface type reference geometry is domain exterior. This can be used to refer to the shared surfaces between the simulation region and the exterior surfaces of the selected domain. You can identify your desired domain from the list of available domains in the objects tree while you are in partition volume mode. Here, for example, selecting domain number 3 will result the boundary condition to be assigned to all simulation region boundaries, since they all have shared surfaces with this domain. By selecting the boundary condition in partition volume mode, you can highlight the areas it is referring to. The next surface type reference geometry is domain-domain. This will consider the surfaces shared between two selected domains as reference. You can identify your desired domains from the list of domains in the objects tree. In our example, I can apply the boundary condition to the interface between the core and the shell by referring to the shared surface between domain number 1 and number 2. You can now see that the boundary condition is applied to the interface between the core and the shell. In addition, we have the option to select a domain as a surface type reference geometry. This will create a reference geometry referring to all surfaces of the selected domain. For example, here I select domain number 2 as a reference in order to apply my boundary condition to the interface between the core and the shell. This is because this interface and domain number 2 surface are essentially the same. The next reference surface type is solid, which refers to the surfaces of a geometry object in the objects tree. If the object has both inner and outer surfaces, checking the option outer surface only will only consider the outer surface of the object as reference. In our example, I can apply the boundary condition to the interface between the core and the shell by referring to the core as a solid reference. Note that here the core object doesn't have any inner surface, so checking the option outer surface only won't make any difference. Another available surface type geometry is simulation region. This option can be used to refer to the boundaries of the simulation region. Here, for instance, I can apply my boundary condition to simulation region boundaries in the x direction by selecting x minimum and x maximum options. The next surface type reference geometry is solid simulation. This will consider shared surfaces between a solid object in the object tree and simulation region as reference. This option is not applicable to our example since there is no shared surface between the solid objects and the simulation region. Also available as a reference geometry is a material option. This option can be used to refer to the interface between the areas occupied by the two selected materials. The materials can be selected from the list of materials under Materials group in the object tree. Here, for instance, I will apply my boundary condition to the interface between core and shell objects by selecting the core and the shell material available in the objects tree. The last surface type reference geometry is called surface. This will simply consider the specific surface selected from the list of domain surfaces available in the simulation region. You can identify your desired surface by browsing through the list of surfaces in the objects tree while being in partition volume mode. In our example, I can apply the boundary condition to the interface between the core and the shell, which is identical to surface number 2 as reference. The second major type reference geometry is volume type reference. There are 3 different volume type references which you will get familiar with shortly. I will use a doping profile object as an example to demonstrate the application of volume type reference geometries. The first volume type reference geometry is called solid. This will consider the volume of a selected solid object as reference. The object can be selected from the list of geometric objects available in the objects tree. For example, here I can assign a doping profile to the shell object by selecting it as a solid type reference. Selecting the doping profile object while in partition mode will highlight the area that the doping is assigned to. Another available volume type reference geometry is domain. This will refer to the entire volume of a selected domain as reference geometry. In our example, I can apply a doping profile to the shell object by selecting domain number 1 as reference geometry for the doping profile object. You can now see that the doping profile is applied to the shell. The last volume type reference geometry is called all domains. Selecting all domains as reference will cause the corresponding object to be applied to all the domains seen by the solver. This means the entire simulation region is considered as reference geometry. Here, it's obvious that my doping profile is applied to the entire simulation region as a result of selecting all domains. We hope that this video was helpful in getting to know the concept of reference geometries and its applications.